Alright, this 8.3 is the last section in the chapter 8. So in this section, we're going to still talk about the formal testing, formal hypothesis testing, but this time we will test a claim about the mean, the mu. Okay, so first we will talk about the test about population mean. So that means we are testing about the mu value. So part 1, we will talk about the realistic common used case in this test, which means sigma is not known. So we will say it's almost impossible to get the value of the sigma, the population variance in the real world problem. So this will be the most of the case. But part 2, we will just talk a little bit about the rare case when sigma is known. Okay, we will focus on the part 1 and because the cases with sigma known is really very rare. So let's check the objective. We will talk about the formal hypothesis to test the population mean mu. Okay, so the previous 2 sections we focus on talk about the hypothesis test about the proportion, but here we'll talk about the mean value. So let's check the notation. So the sample size is to the n. So how many samples in our experiment? That's the sample size. So the sample mean, we already know it's the x bar. It's from the sample, right? And the s is the standard deviation also from sample. So it's the sample standard deviation. So I would say the part 1, we focus on the case sigma is unknown, right? So we're going to use the sample standard deviation. Because sigma is unknown, so we need to use sample standard deviation, S. And the population mean is the mu. So before we do any test or we do the confidence interval, we always need to check the requirements. But in your test or the quiz, you don't have to check the requirements, okay? But let's check what's the requirement. The requirement is always need the sample is a simple random sample. So randomly selected some sample from the population. That's the basic. Let's check, and the second condition will be we have 2 parts of this one. The first one said the population, the original population is normally distributed. So if we have the information about the original population and we know it's normally distributed, then any sample size will be fine. Remember? But if we do not know anything about the original population, or we know it's not normally distributed, but we have the sample size is greater than 30, then we can still do the testing. And you should be very familiar with these 2 requirements, something like the n greater than 30 or normally distributed, right? It's just the same requirement when we talk about the central limit theorem. So next one will be the T formula, T distribution. So here the formula is not shown properly. Let me see. The first one will be the sample mean, and the second will be the population mean. Again, the first term will be the sample mean, x bar. The second term will be the population mean, mu. Of course, we could still use p-value method and the critical value method to do the test and draw the conclusion, right? But make sure you know here we are talking about the t-distribution. We are doing the t-test. If we gonna use the t-test, t-distribution, when we check the table, we should know we need one more value. It's the degrees of freedom. And how can we get the degrees of freedom? It's still n minus 1. Okay, the same rule. When we check the critical value, when we check the p-value, every time that we're going to use the t-table, we're going to use the t-distribution, we always need to know what's the degrees of freedom. It's not like the z-table. Z-table, you do not need the degrees of freedom. But for t-distribution, t-table, you always need the degrees of freedom. Okay, let's check the normality, requirement for normality. So we just quickly go through this one. Sometimes we know the original population is not normally distributed. Then we will say we need this condition. N is greater than 30. If N is greater than 30, then any kind of distribution is fine for the testing. But sometimes the original population is not perfectly normally distributed. It's not perfectly normally distributed, but it's not far from the normal. Then we will say it's not necessary to get the sample size greater than 30. The sample size 15 to 30 may be also sufficient for the testing if the original distribution is not far from the normal. Okay. But if it's greater than 30, that will be perfect, right? So this is a quick review. When we talk about the confidence interval for the mean value, for the mu, we also talk about the properties of t-distribution. So this is just a quick review because that's the same distribution, t-distribution. So is different if the sample size is not the same. So the t-distribution is different for different sample size. If n is 30, we have the t-distribution. If n is 300, we have another t-distribution. The shape is not exactly the same. But no matter what's the degrees of freedom or what's the sample size, the t-distribution is still the bell-shaped curve. That means it's still the normal distribution. T-distribution is also a normal distribution. But its wider shape reflects the greater variability. So remember in our formula we use S to estimate the sigma. So which means we do not know the sigma value. We're going to use S to estimate sigma. Okay, so the mean of the t-distribution, just like the z-distribution, is also equal to 0. So no matter t-distribution, z-distribution, the mean is the same, is 0. But the standard deviation of the t-distribution is greater than 1. Is greater than 1. Remember, when we talk about the z-distribution, the standard and normal distribution, the standard deviation is equal to 1. But for t, is greater than 1. And the last property is when the sample size gets larger, then the t-distribution will get closer to the z-distribution. So if the sample size is very, very large, then the shape will be extremely close to the standard normal distribution, z-distribution. So let's check the example here. Let's check the example. So in this case, we have several useful information, right? So we know the sample size here, n is equal to 12. So we only have 12 values in our sample. And we also know the x bar. How can we get the x bar? We add up all these 12 values, then divided by 12. That's how we get the x bar. X is just from the sample, right? And we can also use the sample values to get the standard deviation. So that's our S value. That's our S value. It's the sample standard deviation. So in other words, we only know the sample standard deviation. And we cannot find any information about the population standard deviation sigma, which means in this case, sigma is unknown. Sigma is unknown, then we should pick the t distribution. Remember that? Of course, we need to check the requirements. So we know the S value, we know the X bar, and we also have the sample size N. We set the significance level alpha is equal to 0.05. Now, another thing we need to find is the claim, right? Remember when we do the hypothesis test, we always need to have the claim. It's a statement, it's an assumption, it's just a sentence, something like that. So, and here we check the claim. The claim says the mean amount of sleep for adults is less than 7 hours. It's less than 7 hours, the average sleep time, right? The mean sleep time is less than 7 hours. So we have this claim, and we know in this claim we have the word is mean. So which means this time we're gonna doing a test about the mean value, population mean mu. So we are talking about the test about the mu. So before we do the test, we always need to check the requirement. Remember, the first requirement is the sample should be a simple random sample. So if the sample are randomly selected from the population, then that sample will be a simple random sample. So the first sentence already tells us randomly selected subjects. So it's a simple random sample, but the second one, that will be the problem. Let's see. The second requirement is either the population is normally distributed or the sample size should be greater than 30. But when we check the sample size in our case, we realize the sample size is not greater than 30, right? It's less than 30. And we do not know any information about the original population. We do not know if it's normally distributed or not. So maybe we could draw the curve, draw the histogram, draw the plot to help us test if the original population is normally distributed or not. So here we use the software to help us draw the curve. And from the curve, we will get to this conclusion. The distribution is approximately normal. So the normality condition when we do the test about mean value is not very strict. So we will treat this case as the both requirements are satisfied. So we can continue to do the test. We could continue to do the test. But if you still don't know how to check the requirements, you do not know how to use the histogram or plot to test if the distribution is normal or not. Don't worry about that, because in your test or exam or quiz, you will not need to do this part. Even in your homework, you do not need to do the requirement check. Okay, let's go to the test. To go to the test, the first step we will say we need to find the claim. Right? We need to find which sentence is our claim. We already said that in this case, the claim, the mean sleep time is less than 7 hours is our claim. So after we find the sentence, next step we need to translate the words into a symbolic form. So of course we translate the mean into our mu, right? And less than, we will put less than 7. So we have the symbolic form of our claim. Next step, we will try to figure out this symbolic form is our non-hypothesis or our alternative. It must be one of it. Okay, so the most important part is the sign in the middle of our expression, right? So here we have a less than sign. It's not an equal sign. So it must be our alternative hypothesis. So if this one is the alternative, if this one is goes to the alternative, we could easily find what's the none, right? We only need to change the less than sign to the equal sign. So we will get our none hypothesis. Again, the only possible sign in your none hypothesis is just the equal sign. Okay, and we know mu less than 7 is our alternative. Then we will ask ourselves the question, it's the one-tailed test or two-tailed test? It's left side or right side? So it's less than, so we know it goes to the left. So I will say left, put it left here to remind myself it's just the one-tailed test. So by this step, we list what's the none and what's our alternative. Next step, we only need to figure out what's the alpha value, right? We know the alpha value is directly from your question. Sometimes the question did not specify the significance level alpha, then you always pick 0.05 as the default value. So just like we said, we do not know the sigma. In this case, we only have the value of the S, sample standard deviation. So this is the case. Sigma is unknown. If sigma is unknown, which means we should pick the t-distribution. So that means we should do the t-test. We use the t-distribution, that means we do the t-test. So we're going to pick the formula of t, right? Formula of t. So next step, we're going to use the formula of t. So the numerator should be x bar minus mu. So this is the correct test statistic. I'd like to put a star here, so to show me this is the test statistic. So we know this is the correct formula to get the test statistic. Let's check the top. The first value is the sample mean. So we know the sample mean is from the sample. So here we have this 6.83. And the second value is the mu value. Again, how can we get the mu? Because we do not know the mu. But when we go back to check the assumption here, we have the non-hypothesis here. The non-hypothesis tells us we assume mu is equal to 7. We have this assumption. So when we do the test statistic, we're going to just use the value in our assumption. So mu is just equal to 7, right? Then we check the denominator here. Denominator is also from your sample. We just use S to estimate sigma, because sigma is unknown here. We're going to use S. So here is the S. And the sample size is just N. Is just how many values in our sample is 12. So after that, we use the calculator to get the value of test statistic. But this time we are doing the t-test. So our test statistic is a t-value. So t star is our test statistic. And we have this is negative 0.29. We will use the t-table. Okay, So let's check the p-value if we use the technology. If you don't know how to use the technology to do the test, it's totally fine. But you should know how to check the output, right? So we know we need to check the output to find the p-value. After that, we can make the decision. We can draw the conclusion. So you can always find the p-value by using the technology. Okay? So we will focus on how to use the table to find the p-value in our class. But we know from the output, we know the p-value is 0.3887. So it's definitely greater than alpha, right? Because alpha is 0.05. If p-value is greater than alpha, we will fail to reject our none. Of course, the last step, we need to interpret our conclusion into the non-technical form. We will conclude no significant evidence to support the claim. We will say this claim is still correct. So we do not have sufficient evidence to support the alternative. Alternative here is the original claim, less than. So no sufficient evidence to support this alternative, less than 7 hours, because we failed to reject it now. So we will talk about the p-value method without the technical. So that's the most important part. We're going to check the table to help us to find the p-value. But not like the z-table, we're going to find the exactly p-value. When we check the t-table, we only can find the range of the p-value. We cannot find the exactly p-value. We cannot find the exactly area, but we could find the range. This range is already enough to help us to draw the conclusion. Okay, so let's see why we could not find the exactly value of the p. So when we talk about this case, we have t is equal to negative 0.29 as our test statistic t. So we're going to use this one to check the t-table, right? So if you check the t-table, you realize we only list the positive t-value and not all of the value. It's just part of the t-value in our table. The body of this table just lists the different t-value, but very limited, and only list positive value. We have the negative test statistic here, but it doesn't matter. We only focused on the value. Just ignore the negative sign to check the table. So we use 0.29 to check our table. And we also need the degrees of freedom. Degrees of freedom here is 11. So first, we're going to check the degrees of freedom. We check the left column. We find the degrees of freedom 11. It's the whole row, right? It's the whole row. But when we check the values in this row, we realized no one is exactly 0.29. The largest value here is 3.106. It's the very left one. And we goes to right side, it goes smaller and smaller, but the smallest value in this row is 1.363. It's still not 0.29, but we can sure the value 0.29 is even smaller than 1.363, which means it's even right to this value. So we know it's even right to this 1.3. So we check the top row of this table, area in one tail. The value there is 0.1. So which means the area in one tail for 1.363 is 0.1. But our value 0.29 is right, even right to this 1.363. So our area is even goes right to this 0.1, right to 0.1. But we realize area goes to the right, we will get a greater area than 0.1. So it's almost impossible for us to get the exactly value, but we could get this range. The right to this value is getting the area greater than 0.1. Again, you find from the left to right, the t goes smaller and smaller, but when we check the top row, we know from the left to the right, the area in one tail gets larger and larger. So if it's 0.29, it's right to the smallest number, then the area will be greater than the largest number, 0.1. Make sure you check the t-table very carefully. This time we could not find the exactly area. We should find the range. After we know the range, it's still possible to help us to draw the conclusion. We know the p-value is greater than 0.1. Then we realize it's definitely greater than our alpha value, 0.05. So it's greater than 0.1. Of course, it's greater than 0.05. We could draw our conclusion. We say we fail to reject none. Again, p-value is greater than alpha. We fail to reject none. So next method, we call it a critical value method. We still gonna find the critical value by using the alpha, because we are doing the one-tail test, because it's just the left tail test. It's a one-tail test. We could directly use the alpha value to find the critical value. So this time we'll go to the t-table. We check the top row first. We check the top row. We know the alpha is equal to 0.05. So we find the area in one tail is 0.05. Then we find the whole column, right? But which one is the value we're going to use? We still use the degrees of freedom. We find the degrees of freedom 11 and the column for 0.05 in one tail. We find the critical value in your table is 1.796, but actually the table only provides you the positive value, but we are doing the left-tailed test. If you check this curve, you will realize the rejection region for left-tailed test is on the left. So the critical value is also on the left. Actually, the critical value here is the negative 1.796. It's the negative 1.796. So the actual critical value should have a negative sign. Okay. Again, left side test, you have a negative t-value as your critical value. If a right tail test, you have a positive critical value. And if you are doing the two-tailed test, then you have two, positive and a negative. So after we have our critical value and we know the test statistic, we could use this to draw the conclusion. If you check the rejection region, you will find the position of your test statistic is here. And the critical value is right here, you realize the test statistic is out of the rejection region. So out of the rejection region, we fail to reject. Or you could use my method. Just compare the absolute value of these two t's. You realize the test statistic has the smaller absolute value, then we fail to reject none. Then the same thing, we still fail to reject none. Okay, so we'll talk about a little bit the confidence interval. So when we talk about the confidence level and the alpha level in chapter 7, we talk about the confidence level is just 1 minus alpha. But here, we should know it's not always the case. It's not always the case. In this example, because we are doing the one-tailed test, actually we are doing the one-tailed test, left tail test, which means the left tail we should have 0.05. That's our alpha, right? And because we are talking about the confidence interval, it always has two-sided. If the left side have alpha, the right side should have the same thing, also have the alpha. Then the confidence level in the middle will be 1 minus 2 alpha. So in this case, if alpha is equal 5%, but the confidence level is not 95%, it's the 90%. Because left tail 5%, we also need to list right tail 5%. Then in the middle, we will get 1 minus 2 alpha. It's 90%. So if you want to construct the confidence interval, make sure you can only construct the 90% confidence interval for this case. So if you use the same procedure we learned in chapter 7, we could get the 90% confidence interval just like this. So we can use this confidence interval to try to draw the conclusion. We know in our none we have this assumption mu is equal to 7. So we use this value to check the confidence interval. We realize 7 is included in this, right? In this region, is in this interval. So within the confidence interval, 7 is included or contained within the confidence interval. So we will say we fail to reject. We fail to reject. We do not have sufficient evidence to reject this null hypothesis. We fail to reject. So here, in this case, the confidence interval method draw the same conclusion as previous two methods, critical value method, p-value method. But I would say we're gonna still recommend to use p-value method and the critical value method to do the testing. And for the confidence interval, just for estimating.